So, welcome to Fault Masterclass, and this is a key area, lots and lots of questions associated with this. You can see a photograph on the right hand side that's just popped up, and there's some key features we can identify. With any fault, you've got a fracture. You can see me drawing the lines on that indicates that that area has undergone some stress. Now, the type of stress we'll have to investigate later, but those two things that I've just identified on there, these are our fault planes. So they are clearly visible and clearly going to be identifiable. You can see some semi-horizontal lines, shallow dip, and these are the actual bedding planes. Okay, and we can also see a marker bed. So this is M. There's one here and here. Okay, and we can see the direction of movement on there, or displacement is the term really you should be using. That has moved down and that has moved down. So we should be able to work out what type of fault it is, how much movement or displacement has been involved. The diagrams at the top are obviously going to be there to help us. So you can see up here you've got your dip slip fault, or your normal fault, and your reverse fault over on this side here, and they are characteristic types of faults that you need to know. And then below you've got your strike slip faults. So key thing first off is, are you looking at a map or are you looking at a diagram? And you can clearly see on the bottom photograph it's like a diagram point of view, and these diagrams above are showing that the movement as well. So the first thing is, is there vertical displacement? Okay, so a dip slip fault basically means that there is the fault plane is going to be at a relatively steep angle, and that is going to be absolutely key to working out what type of fault it is. So with the photograph, this one here, you can clearly see that has slipped vertically, and if it's lateral, obviously it's moved sideways. So with these strike slip faults, they often displace intrusions, which you can see on there, and that might be a dike or a sill which has been moved sideways or laterally. And you can see on the diagram here that you've got a line of trees. So I'm just putting those on there. That's clearly been displaced. So this little geyser on the side here can see that has moved in a left-hand manner, which is the sinistral or the left type of movement. On the right-hand side here, you can see that the trees opposite the fault plane. So there's the fault plane. Line of trees there, it's moved to the right, so that is a dextral type of movement, and they are strike slip faults. That fault plane, which I've just drawn on, and I'll draw one on the other one as well for you, is vertical. It's a vertical fault plane, so that is key to working out what type of fault that is. Dip slip faults a little bit different. Dip slip faults are very, very common, and it's all about the fault plane being at an angle. But know the other characteristics. The two key ones that you really, really need to know are the hanging wall and the footwall, and basically whether they've moved up or have they moved down. Now, to do that, the little diagram is the best way I think to do it. And you can see on here, we're clearly looking at a cross section, because you can see the little guy at the top. And we've got some displacement, and we've got a marker bed here, which is M. Now you can see at the top that I've indicated an angle, so my fault plane will be at an angle, and what you look for is the smallest angle and the largest angle. The largest angle there at the top indicates that is the footwall. On the right hand side here is the hanging wall. Now you can see the displacement here. We could be asked to measure that, and if it's vertical displacement, that would be the throw. Now that side, the hanging wall, has moved down, so that is also the down throw side. So if the hanging wall moves down, that is a normal fault. If the hanging wall moves up, that's a reverse fault. It's just a rule you've got to remember, and it should help you identify those. So we can see up here in the diagrams that that is identified for you. So you can clearly see that we pick a different colour, maybe an orange. You can clearly see that this angle here is the largest, so this is the footwall, F for footwall. On this diagram, the largest angle is on this side, and that's the footwall. So on the reverse fault, the footwall has moved down. On the normal, the footwall's moved up. It's also created this area here. If I just show you, so this area on the diagram here, so this part has been exposed. That is called a scarp. Now that is characteristic because you've got the hanging wall has dropped down, so it's exposed that sort of little that area of rock. On this one, with the hanging wall moving up, here's our hanging wall, it's almost created like an overlap here in this area. So the footwall always has the largest angle, or the larger angle. Just mentioned that, which is absolutely key. Don't forget about that. And if the footwall moves up, it's a normal fault. So here's my fault plane, just to give you a different way of testing this in an exam. My largest angle is going to be here, and this is my hanging wall. My hanging wall drops down, that's a normal fault. If it moves up, it's a reverse fault. Simple as that. Faults always will show some sort of displacement, and that's the word that you should be using. And if we're measuring the vertical displacement, as I've said before, that will be the throw. So back to my diagram, if you wanted to measure the throw, it's always from the marker bed, so you need to find one of those first, obviously. And if we go from the bottom of this marker bed and we just draw a line straight down, it's quite hard for me to do there, to the bottom of the other bed, and we extend that out, that distance there, okay, this bit, I'll just hold it up closely, you can see it there, that little bit there is that's the throw. Okay. Next, this is an easy one to identify really. If the fault has an angle of dip less than 45 degrees, so that's the fault plane. So if we go back to this and we take our protractor and we hold it, to the horizontal, so basically upside down, you can see that the fault plane there, if I'm holding it on there, is about 65 degrees. That's clearly not not less than 45 degrees, so it's definitely not a thrust fault. Now, quite easy to identify. Now, we've got to, they'll often ask a question about tension as well, so or what stress is involved. So if it is tension, as is this case here, or the pulling apart, they are normal, and you can test that, because if you put your hands together and you pull apart, so you move your elbows away from each other, this section here will drop down, okay? And this is the hanging wall. If I want to make them into a reverse fault, all I've got to do is push my hands together, and look, my hanging wall moves up. So that's a reverse fault, and that's one of the ways that you can test if you're right or not. Compression, reverse, hanging wall moving up. And two other things which I just failed to mention quickly is the extension of the crust. Crustal extension or tension is related to mid-ocean ridges pulling apart. That's going to create something like a normal fault. If we're looking at crustal shortening, we're looking at fold mountains, yeah, crumpling the crust up. It's reducing the size of that particular piece of crust. One of the questions that's very, very common, of course, is principal stress. Okay, and this is usually identified by a lambda symbol. Okay, I'll show you that on the next slide. But for reverse faults, the stress direction, because it's compressional, so it's pushing these together, is going to be horizontal, so that the principal stress is that way. For a normal fault, it's the opposite, because this is moving down, the principal stresses are vertical. Yeah. Okay. The faults also, you could be asked about any associated features, so make sure you look up and you have a look at these two terms, fault breccia and slicken sides. I'm not going to go into them. Breccia is broken rock, usually appears on the fault plane, and slicken sides, they look like large cracks, but you need to know a little bit more than that, and you need to be able to recognise them. The final thing, which is really common when you're looking at your geological history, is reactivation. Now, faults can show different types of movement over different periods of time, because geologically speaking, we might be talking about a very, very long time. So, for example, the sequence here on the right-hand side, we can clearly see that this marker bed has dropped down, and it's dropped down this side. So that is the largest angle, and the smallest angle is on this side. So, you know, this is the footwall, and this side has moved down. So, you know, that's a normal fault. And then you've got another normal fault, which is just here, next to it as well. Now, that in the future might show reactivation, and this side might actually move up. It could happen. And that's what we mean by secondary displacement. So the next slide goes into the stress directions. So I'll see you on the next slide. Okay, so this part is about stress, and I'm not going to talk too much about it, but you can clearly see that we've got our normal faults here, and the principal stress, or the lambda max. Okay, so you can see the symbol that you need to be using, or you may come across in the exam, and the principal stress components. You'll also see the minimum stress component, which is in blue. Now, there's also intermediate stress, obviously. The principal stress, therefore, in normal faults, as you can see here, is this direction. So, you know, vertical. I've already said that on the last slide, moving down. To understand it, really, I think, you know, if we think about thrust faults and reverse faults, it's easier, because thrust faults are associated with mountain building and compression. So if we do that, okay, we're creating a force which is horizontal, and that's the principal force which is going to, you know, bend and crumple the crust up. All right. Now the minimum stress component in this case is going to be vertical, and then the intermediate is shearing. For strike slip faults, it's really straightforward. It looks more complicated, but it's a shearing motion. Okay, so it's a lateral amount of movement, and you're going to have your minimal stress components are going to be horizontal and vertical. It's actually going to be shearing side by side, yeah, like that. So that's stress in a nutshell. That's quite a good revision set of diagrams there. And one of the things that I did want to mention is, and I think I have very, very briefly, is that normal faults, as our tip, are associated with mid-ocean ridges. Yeah, the opposite would be the case for reverse faults. They would be associated with mountain building, or like the Himalayas or something like that. So the classic example for normal faults on land is the East African Rift Valley, which has a Horst and Graben structure. Okay, and I think you can see part of it here. So what we've got is a series of normal faults here. So these sections sort of dropping down step by step, and we would have seen them in Iceland if you came to Iceland. There was a similar rift structure, and it's the same on this side over here. This section here has moved down, and this section has moved up. So there's a rift valley, and if we move those two sections apart, the middle section will drop down. Okay. So as you can see at the top, these components can be on all three of your exams. They might be on component 3 in the colour map section, component 1 on the simplified geological map, or they might be in the form of like a box diagram like these here, where you might have to complete a sequence. So A is a box diagram showing, you know, three-dimensional thinking. B is your view from above, so that's your map view, and then C is your cross-section there. You can clearly see that we've got movement along our fault plane. This is the largest angle, so this is the footwall, and the footwall in this case has moved up, and the hanging wall has moved down. So this is a normal fault. Now, to help us interpret this, we can think back to the rules that I gave you when we were looking at our map skills, and what it says is that in dip faults, where there are two beds in contact across a fault, so we've got our fault plane in blue, which is identified there. So this section here, if I just do that, that's our fault plane. Two beds are in contact. The younger bed is on the down throw side. So the youngest bed in the sequence is this one here, which I've just put a Y onto. Now, this is the fault plane, and this is the fault on the map. Yeah, that's where it would be. So the youngest bed here is on the down throw side. All right, this is older, okay, because it's beneath Y. Yeah, so this sequence is clearly older, and that follows that rule. So if we look on this map here, the actual fault runs along here. Yeah, so this is our fault, and this is younger bed, and this is older material on this side. Okay, so and then this is young again. So that clearly is the down throw side. Even if we couldn't see this cross section here, we could use the map to work that out. And you can do it again here. Look, this is the youngest here, young. This is young up here at the top. This is older, yeah, material. So clearly, again, this is the down throw side. So we can use it to identify the fault, okay? And that's quite a good rule to use. The other rules here to do with strike faults, these ones can also be useful, but I just wanted to show you that first one because I think it's really, really useful. Okay, so this section is all about exam skills, and you can see that fault questions are pretty much always related to some sort of relationship. So geological history, measurements that you might need to take, accuracy is going to be really, really important. With this particular sequence here, there's a cross section, so we know what point of view we're looking at. And we've got some other bits of info here. So clearly we've got it related to some fossils. Now, first question, really straightforward. It's asking for the dip direction. Now, dip direction, lots of you, in the past have made mistakes where you've given two directions. Well, dip direction is only one. So it's going to either be east or west because we're looking from the side. So you need to make that choice, but you can use a protractor. Hold it up that way to work out, the angle of dip. But if I just indicate what I would be looking at on here is clearly we've got a smaller angle there and a larger angle here. We can make our own sort of horizontal line along here if we want. So that's what you're going to be measuring. The angle and the dip direction. So really straightforward, nice question. You should all be getting marks for that. And then the second part, it says explain, so we need to give some reasons. One piece of evidence from figure 3a, so this one up here, which confirms that the rock sequence has not been overturned. So it's related to way up again. We've got some dates at the top, so we've got 20,000 years and 100,000 years. We've also got this idea of quaternary river deposits. We've got Jurassic limestone, Jurassic shale, Triassic limestone. That should really be helping you because you should know your time scale, and you should be able to use that to work out the age. The other question here, which I wanted to focus on, is the type of fault shown in figure 3a. We should be able to work that out because I've just given you the key points in the tutorial. So remember the size of the angle, yeah? Remember which is the down throw side and which is the up throw side. I'm just going to put some displacement arrows on there for you. We should be able to work out what fault that is. And your reason has to be related to the hanging wall or the foot wall. And this is the hanging wall on this side and this is the foot wall on this side if you hadn't worked it out already. So I'm going to leave you to have a go at that and have a look at the mark scheme on the next slide. Thanks. So here's the mark scheme. Have a look at it, compare it to what you wrote, and I think it's pretty obvious, you know, and straightforward set of questions. Okay, so this is just another example I wanted to show you very quickly because it's a map view, yeah, and it's the one that really gets people. All right, so we are not looking from the side, and it looks like we could possibly be, but again, look, they have clearly stated this is a geological map. The land area is flat, so we don't have to worry about any contour lines or anything like that. We've got some dip of beds. We've got a younger to older sequence as well. Okay. The other thing, of course, is that we know F2 is vertical. All right. So I've already told you about that. You know, vertical. So does that mean it's a dip slip fault or a, you know, strike slip fault? How would we work that out? Well, one of the things to look for, if I just show you very quickly, is this. So this is one key bed here, and on the other side of the fault, this is the other key bed. Does that thickness between those 2 points change on either side of the fault? Doesn't appear to. It looks to be identical. If the thickness does not change, then the movement is lateral. Yeah. So that must mean that is some sort of strike slip fault. All right. That's a key point that they've put in there. All right. The other thing, obviously, you've got scale on there. We might need to use that. And for F1 over here, it dips at 18 degrees towards the southwest. So it's dipping in this direction somewhere under the surface like that. Now, that's again important because that tells us that it's going to be a dip slip fault probably. Now, before we go any further, you can confirm that because look, the thickness here between this point, this bedding plane and this bedding plane here is much different to this side. Yeah, that clearly shows that there's been some sort of vertical displacement. Otherwise, it would be the same thickness, and so that should help you. There's some statements underneath. It's asking you about the folding actually in here, so I'm going to let you have a go at that, but hopefully you'll be able to figure it out because we've got some dip arrows here and here, and one of them, you know, is dipping at 60 degrees and they're dipping towards each other, so you can start to think about what it might be, and I'm hoping that you'll be able to work that out. We can check it against the mark scheme on the next slide anyway. And then it says draw the axial plane trace of the fold east of F1. So basically we need to draw the axial plane in this direction. Yeah, so it's going to be a solid line. Now, axial plane should go through the core of the fold. If you've done your folding tutorial or masterclass, you should know that. So I would be putting it somewhere here. Okay, and then it's been displaced as well. So it's going to be where those orange lines are, and you can check that on the mark scheme afterwards if you want. The final part, which is B, it says fault F1 involves vertical movement, so it's also telling us, yeah. So we're looking at normal, reverse, or reverse thrust, and it says that it's a down throw to the east. All right, so what they're saying is that easterly. This is the down throw side, and this is the up throw side. Well, that's moved up, that's moved down. And basically it's asking for state the evidence that that has moved down and that side's moved up. I've actually given you one of the pieces of evidence, and it's to do with the thickness. You just need to state that and see if you can think about another piece of evidence which would support that as well. And the final question here is F1 is a thrust fault. The evidence for that from the diagram too. So I'm hoping that you're going to also be able to identify that. If you're not quite sure, you can always have a little look at the mark scheme, but see if you can figure it out first, because they have given you some evidence. It's in here, this bit. Have a look. Okay, that's it. Okay, so this is related to the same question. I'm not going to give you too much help because I want you to be able to have a go at this yourself. But question C at the top there, F2 shows only strike slip movement or horizontal movement. Describe one piece of evidence. If you listened to what I said earlier, you should be able to do that now. And then the second part says measure the amount of horizontal displacement. So make sure that you are doing this accurately and you are using the key. I would use a piece of paper. This isn't a piece of paper, but you get the same idea, and I would be measuring the distance on my piece of paper, okay, and then I would be holding that up against the scale and ticking off how much it's moved, because if you try and use a ruler, you can make some mistakes in there. So use the paper trick that I've taught you about. So amount of displacement and then the direction of movement. So on to D. A student, this is a very common type of question. You've seen these before. You've got to evaluate their conclusions. Basically, are they right or not? And that's a key skill to be able to do. So they have said that the geological structure shown in figure 4 are the following. The fold and fault F1 were formed at the same time and by the same type of stress. Okay, so this is a relation to stress component, and we need to think about that. So the fold we know is formed by compression, yeah, because they all are. Fault F1, is it formed by compression? Well, they said earlier that it's a thrust fault, and it's dipping at 18 degrees. So, and that is a reverse thrust fault. That's formed by compression. So we should be able to agree with that, surely. And you can put it in your own words and check it against the mark scheme. Is F2 is younger than F1. So F2 here is younger than F1. Well, the two do not come in contact with each other. Clearly they are both younger than the folding because they cut across. We've got a cross-cutting relationship between ETUs. Do we have enough information? They don't come into contact with each other. So F2 and F1, can we tell? Would be my question to you. See what you think. Come up with a conclusion. Check it against the mark scheme.